This is Donna Nelson at the University of Oklahoma. So today we're going to continue with the reactions of carbonyl compounds at the alpha position. So we're going to be looking at reactions of enols and enolates. And this is the second lecture for chapter 21. And we're going to now be looking at alpha halogenation of enols and enolates. We're going to start aldol reactions. So let's look under acidic conditions. First, we're going to consider the reactions under acidic conditions, and then we'll go on to basic conditions. So under acidic conditions, ketones and aldehydes undergo alpha halogenation. So here we see acid and bromine, and you can get monobromination. This works with chlorine, bromine, and iodine. So since we're using acidic conditions, an enol is the reactant intermediate. You would not have an enolate reacting under acidic conditions. So here's the mechanism. You've seen this top step before. So this is simply the enol formation where you have proton transfer, you have protonation of the carbonyl, and then you have positive charge formed at the carbon in this resonance structure. Here you deprotonate to regenerate the hydronium ion, and now the double bond has migrated down here. Remember, these are two different tautomers, not resonance structures, the keto and enol form. So there's the proton transfer mechanism. The next step is the actual attack up on the electrophile. So in this case, it's molecular bromine. The pair of electrons in the double bond attacks one end of the bromine molecule. The other bromine atom departs, taking with it the pair of electrons in the bromine-bromine bond. And so you have bromide as the counter ion, and this is your cation. So here we have an oxonium ion. Then you simply have water come in, deprotonate to give you the brominated carbonyl, brominated at the alpha position. So this is bromination at the alpha position under acidic conditions. When an unsymmetrical ketone is used, you will have bromination at the alpha position that bears the substituent. Even though this gives you the more sterically hindered product, it's going through the more stable, and this minor product would actually be the more stable product. But the reason for this, the generation of the less stable product, is that you're going through the more stable intermediate. This is the more stable enol because this is the more highly substituted double bond. So you go through the more stable intermediate and you wind up with a less stable product. So this provides a two-step synthesis for the synthesis of an alpha-beta unsaturated carbonyl. This is an alpha-beta unsaturated carbonyl. So remember that the end of the first step here is going to be functionalizing the alpha position with bromine. Then add pyridine. The pyridine functions as a base. It comes in, removes a proton here, generating a double bond, and bromide departs. So that is how the unsaturation is formed. So this is an alpha-beta unsaturated carbonyl. You can use other bases here, such as T-butylithium, T-butoxide. Notice that these, or carbonate, dilithium carbonate. So notice that these bases that are used are sterically hindered, and there's a reason for that, because you want the base that is used to function as a base and not a nucleophile. You do not want to have attack at the carbon of the carbonyl. So use a large base here to simply remove this proton and not attack as a nucleophile at the carbonyl carbon. So this named reaction, Held-Volhard-Zelinsky reaction, HVZ, brominates at the alpha position, and you have seen how you have bromination at the alpha position to a carbonyl, but this is an interesting reaction because it converts, the first step is that it converts the carboxylic acid to an acid bromide. So this is an acid halide, so this is an acid bromide using phosphorus tribromide. And so here you have the acid bromide generated. This first step we're not going to cover too much. It's similar to forming an acid chloride using thionyl chloride, as you saw in the previous chapter. And so it's an analogous reaction, except here you formed an acid halide. This reaction does not work with acid chlorides, only with acid bromides. And so now, remember, you can always have, when you have a carbonyl, if you have alpha protons, you can have the enol formed, and that is indeed what has happened here. You have the enol formed, and once you have the enol formed, you can brominate at that position. And so that is what has happened here. Then, remember when you have acid halides, they're very reactive, and so adding water to the acid halide regenerates the carboxylic acid. And so although this has several different steps here, the overall reaction is that you have simply functionalized at the alpha position. And without the explanation, you might not realize that it's gone through the acid bromide, and then the acid bromide is the one that is actually being brominated at the alpha position, and then the acid bromide is subsequently converted to the carboxylic acid. Once again, alpha halogenation. This time it's under basic conditions. And here we have the bromination is occurring at the alpha position. Now, notice you have this alpha position also, and you might start thinking, well, this would give me a more highly substituted double bond, but you have no alpha protons over here. So this carbon is not going to be involved in any reaction. You have no alpha protons. The only alpha protons are on this side of the carbonyl. So the chemistry will be done at this carbon. And I put in a couple of extra arrows because you're going to see this product taken further in subsequent slides. So you might want to remember how this was generated. So you have simply brominated at the alpha position by going through the enolate, and then the enolate attacking at the attacking bromine. And so here this is, this mechanism is for this reaction. So you simply deprotonate here at the alpha position. You generated the enolate, the negative charge, the pair of electrons involved in the negative charge attacks bromine, and molecular bromine, and bromide departs, carrying with it a pair of electrons and the negative charge. Now, using the product that I told you about, that product, monobromination, can undergo a subsequent bromination because you do still have another alpha proton, and so you can get dibromination at that position. Methyl ketones, here you're going to have, on this side you have no alpha protons, over here you have 3. And so the fact that you have 3 alpha protons becomes important because all 3 of those alpha protons can become brominated, can be replaced by bromine. So you have the alpha position here, the alpha carbon, can undergo bromination 3 times because you have 3 alpha protons. And once the CBr3 is formed, then that becomes a good leaving group. Just like in your previous chapter, you saw carboxylic acid derivatives where the group that was attached to the carbonyl can become a leaving group, and that's what happens here. So let's look at this mechanism. Once you have bromination occur 3 times at that methyl group, because this, when you have the methyl there, that's 3 active CH bonds. Each one can be replaced by bromine. Now what happens is you have the CBr3 at that position. Hydroxide, remember this is under basic conditions, can come in and do a nucleophilic attack just like a carboxylic acid derivative, where this is a good leaving group. So it does a nucleophilic attack, then the pi bond is reformed, and CBr3 departs. Now this is a good leaving group because this easily bears a negative charge. It's carbon bearing 3 electron withdrawing substituents. And then you know that carboxylic acids are acidic, and so the CBr3 deprotonates the carboxylic acid. And so you have the carboxylate formed. And so that can be just simply, if the solution is neutralized with a little bit of acid, you can regenerate the carboxylic acid. This is bromoform that you have generated. You're going to be very familiar with chloroform, CHCl3, and similarly, you could generate iodoform, CHI3, in this sort of a reaction. This reaction is somewhat important because if you use iodine instead of bromine, you generate iodoform, CHI3. And iodoform can be easily observed when it's formed in the reaction because it forms beautiful yellow crystals shaped like hexagons, 6-membered rings. And so it becomes a reaction that enables one to identify whether one has a methyl ketone present in their molecule. And so it's good for determining structure identification. So that's iodoform. This reaction is sort of famous. Sometimes it's called the iodoform test for methyl ketones. Okay. This can also be used to generate carboxylic acids from the methyl ketones because the methyl group can be converted into hydroxyl, as you just saw. But over here, you need to have no alpha protons on one side of the carbonyl. So now, we're going to aldol addition reactions. When an aldehyde is treated with hydroxide or an alkoxide, an equilibrium forms where a significant amount of both the enolate and the aldehyde are present. And so when you have the enolate form, that will be where the hydroxide removes a proton here, and you have a negative charge. When you have an aldehyde undergo this reaction, you can have a product called the aldol. So here's the aldehyde, and here's the ol. This is the alcohol. So here aldehyde and the alcohol functional groups are present. So the alcohol functionality will be at the beta position. This is really merely the product of the aldehyde reacting with itself. Notice you start out with 2 carbons in the molecule. Now you have 1, 2, 3, 4 carbons in the molecule. And if you look closely, you can see there's the aldehyde, and here's the carbons of the aldehyde. So you have 1 aldehyde and the second aldehyde carbon skeleton joining together. So you have this carbon attacking at the carbonyl of another aldehyde, and you're going to see that on the next slide. So basically this is the aldehyde reacting with itself. So here on the first aldehyde, under basic conditions, the proton is removed, forming the enolate from the aldehyde. Then this enolate does a nucleophilic attack on another molecule of itself. So you have the carbon at the alpha position, the alpha carbon, doing an attack at the carbonyl carbon. So the new bond is right here. So once again, you can see 1 aldehyde molecule, and there's the second aldehyde molecule. So the new bond connecting the 2 carbon skeletons of the 2 aldehydes is right here. And then a negative charge is generated at this oxygen atom, and so then that oxygen is protonated to give you the alcohol. So here's the aldehyde, and this is the alcohol. 1 aldehyde, and this is the second carbon skeleton for the aldehyde. So you can see the 2 molecules have become joined together at that carbon-carbon bond. That carbon-carbon bond is the new carbon-carbon bond. So this is called an aldol addition. Aldehyde, alcohol addition. So it's an equilibrium process. So both the reactants and the products will be present. So you can usually identify the new bond by looking at the substituents attached to the aldehyde. So 1, 2, 3, this is a 3-carbon chain. 1, 2, 3, there it is. Here is 1 carbon skeleton from the aldehyde, and here is the second carbon skeleton from the aldehyde. So the new bond has been formed here. You can see 1, 2, 3 carbons. 1, 2, 3 carbons. So the alpha carbon of 1 aldehyde has become attached to the carbonyl of another aldehyde. Okay, so here is the new bond. For most ketones, this process is not favored. It's just too sterically hindered. And so you won't see this used very often. It's usually aldehyde, so that's when it's called an aldol reaction. The reverse process is simply called a retroaldol. And since it's an equilibrium, that can be achieved. And so, remember, it's under basic conditions. the hydroxide comes in, removes a proton, a negative charge is generated at oxygen. So a pair of electrons moves in, reforms the carbon-oxygen pi bond, and so this becomes the leaving group. This incipient enolate right here becomes the leaving group. This leaves, it's stabilized by resonance and conjugation, and so now you have the this is a ketone, this is acetone, and the negative charge moves in, the negative charge is protonated by water to regenerate the hydroxide. So this is the reverse process that one would have if you attempted to do this reaction by using a ketone. And remember, we just finished saying that for ketones, this reverse process is more favored because the individual ketones are more favored in that equilibrium than the aldol condensation product is. When an aldol product is heated under acidic or basic conditions, either one, you get an aldol condensation. An aldol condensation means that you've lost water across the alpha-beta carbon bond. So here, this becomes an alpha-beta unsaturated carbonyl. This is the aldol condensation product. Okay, so you've got the aldehyde. You'll have two molecules of this react. So a molecule of this will react with itself, another molecule of itself, to give you the aldol product, and then you'll lose water across the aldol addition product to give you the aldol condensation. So this is an alpha-beta unsaturated carbonyl. And you achieve that with a little bit of heat. Sometimes no heat is needed. So here, this shows you the aldol condensation. Here the aldol addition is. You can see there's the first molecule of the aldehyde. Here's the second carbon skeleton of the aldehyde. So the new bond is formed right here. The alpha carbon attacks the carbonyl carbon. So this becomes the aldol addition. If it's done with a little bit of heat, then it becomes the aldol condensation product, where the water is lost across the alpha-beta carbons. This is the alpha position, beta position. Now it is the alpha-beta unsaturated aldehyde. Here, the hydroxy group was at the beta position. Beta hydroxy aldehyde. So let's look at the mechanisms of these reactions. So a hydroxide comes in, deprotonates at the alpha position. You have the enolate formed. This molecule, the enolate, reacts with another molecule of itself, shown right here. The alpha carbon, which is now bearing a negative charge, comes in and attacks the carbonyl carbon. Here is the new bond. You can see the aldehyde there and there, the carbon skeletons of the aldehyde. And so now oxygen is bearing a negative charge, deprotonates water, regenerating the catalyst, hydroxide, and so now you have the aldol addition product. Now, if it's done with a little bit of heat, sometimes heat is not even needed, now you have so here's the product of the first step coming down here. So now hydroxide comes in, deprotonates at the alpha position, And so now you have an anion at that alpha position. This moves in, forms a pi bond, and you have hydroxide Li. Now, usually you don't have hydroxide Li, but this is done under basic conditions. And so here you have the alpha beta unsaturated carbonyl as the product. So this is the aldol addition. Now this is the aldol condensation. So the condensation is actually when you lose the water. That makes it the condensation. That's the condensation step. So if you can get either the cis or the trans isomers, the one with the lower steric requirements will be the major product. So obviously that will be the trans double bond. The cis double bond will be the minor product. Here, remember I kept saying that it's not always necessary to heat the reaction mixture in order to get the aldol condensation. So this is the aldol addition, where you have this molecule reacting with another molecule of itself. It's deprotonated at the alpha position, and you can see there is the carbon skeleton of one of the, in this case it's a ketone here, so there is the carbon skeleton of one molecule of the ketone. There is the carbon skeleton of the other molecule of the ketone. And so you can see, so this is the aldol addition product of these two ketones. And notice that you have the hydroxide here and a CH bond here. So you can lose water across this bond and generate a double bond right here. So giving you so this will be the condensation step. And so why is this not isolated and this one is? And so this enables you to do the aldol condensation of the ketone. And it's because you have an extended pi skeleton. And so that gives a lot of stability to this molecule, a very stable molecule, making this be not isolated, and this is formed with no heat necessary. So it's situations like this in which heat will not be necessary to get the aldol condensation product. Yields for the condensation are typically greater than yields for the addition reaction. So here, once again, you get the condensation, and this is ketone. You get the condensation because you have the possibility of the conjugation, and also this is much less sterically hindered than this. Okay, so here you've lost this group. This is going to be a planar molecule, nice planar molecule, much less steric hindrance. So that finishes our aldol reactions, and we're going to go on in the looking at more aldol condensations in the next lecture. So that finishes the first part of the aldol additions and the aldol condensations, and we'll look more in the next lecture. We'll look at more of these and some crossed aldol condensations where you're not dealing with an aldehyde reacting with itself. It can be two different aldehydes reacting with each other.